in the last class we have studied about the 2 degree of freedom system. There we have found the equation motion by using Newton's principle or D'Alembert principle. Also we have used Lagrange principle and extended Hamilton principle to derive the equation motion. So in case of 2 degrees of freedom system, we required minimum 2 coordinates to define the motion of the system, and in this case I already told you about 3 different coordinate systems. One is the physical coordinate system, second one is the generalized coordinate system, and the third one is the principal coordinate system. In case of a physical coordinate system, you can fix a physical coordinate or you can fix a reference frame, and from this reference frame you just take the coordinates of the system or coordinates of the point where you are finding or using which you are finding the equation motion. In case of generalized coordinates, so these are the coordinates or minimum number of coordinates required to express the motion of the system completely. In case of a, so already you have seen in the case of a double pendulum, so this is the double pendulum I have already told. So in this case of a double pendulum, you have used x1 y1 x2 y2 as the x1 y1 x2 y2 as the physical coordinates, and this theta 1 rotation of this theta 1 and rotation of this theta 2 as the generalized coordinates. And already I told you, by using these coordinates you can write the equation motion in case of a 2 degree of freedom system, and you can write it in the matrix form. So in the matrix form you can write it like this: m11 m12 m21 and m22 x1, or in this case you can write it equal to theta 1 double dot, or you can write in terms of x1 x2. So you can write it is equal to x1 double dot x2 double dot plus k k11 k12 k21 k22 x1 x2 equal to f1 f2. So in case of free vibration, this fourth term, the right hand side terms are 0, and I told you about the dynamic and static coupling. So if this mass matrix is coupled, that is all the terms are present, or off diagonal, some of the off diagonal terms are present, then the system is said to be dynamically coupled. So dynamically coupled. So in this case, some of the terms off diagonal terms, that is this is the diagonal terms, this m11 and m22 are the diagonal terms. So this one and these two are the off diagonal terms. If these off diagonal terms are not 0, then the system is still to be dynamically coupled. Similarly, in case of the stiffness matrix, if the off diagonal terms are not 0, or if there present some off diagonal terms, then the system is said to be statically coupled. So already you have seen the case of statically coupled and dynamically coupled system. So in this case, to make the system dynamically and statically uncoupled, you can take another set of coordinate system. So those coordinate system using which you can write the equation motion in the uncoupled form, or the system will reduce to a dynamically uncoupled and statically uncoupled form, are known as the principal coordinate system. So the principal coordinate systems are the generalized coordinate system by using which you can write the equation motion in an uncoupled way, or in that case the dynamic matrix and static matrix will be uncoupled. So in that case it will reduce to 2 single degree of freedom system equation, and using these 2 equations you can find the solution of the system. So already I told you about the extended Hamilton principle and Lagrange principle. In case of Lagrange principle, I told you you can use this equation d by dt of del L by del Qk dot minus del T by del Qk equal to Qknc. So here L is the Lagrangian of the system, that is equal to T minus, so this Lagrangian L equal to T minus V. T is the kinetic energy, V is the potential energy of the system, and this Qk is the generalized force which you can find from this. So, in this equation F I is the, so this is F I the force acting at ith station and R I is the position vector of the ith point on this system. So, this Qk, so Qk is the small qk is the generalized coordinates you are taking. So, in this 2 degrees of freedom system k will be equal to 2. So, it will be either 1 or 2, and using this formula you can find the generalized coordinates. And for a system with damping you can use this dissipation energy, this d is the dissipation energy, and using this dissipation energy you can find the equation motion. So, already also I told you about the extended Hamilton principle. In extended Hamilton principle you can write the equation motion by using this equation. So, it is equal to del L plus del W NC dt equal to 0, where this virtual displacement del Qk at T1 equal to virtual displacement at del Qk T2 equal to 0. So, previously we have derived the equation motion of a system. So, these systems we have taken. To derive the equation motion we have taken a spring and a mass. So, the spring mass systems we have taken. So, in the spring mass system one rod is hanging from this cart. So, this is the mass. So, from this mass a rod is hanging and I have retained this point C. So, let C is the position of the mass center or the mass center of this rod. So, for simplicity I have assumed this mass center is situated at L by 2 distance from this. L by 2 distance, let L is the length of the rod, and at L by 2 distance this mass center is situated. So, when it is, so when this body is not moving or when it is not undergoing any vibration, so this is the undeformed position, and the deformed position if I will plot. So, in the deformed position, so this is the undeformed position and you can draw the deformed position. So, in the deformed position the mass is at this position, and so the rod position is like this. So, this is the rod. So, this is the mass center. So, you can have, so this is the spring or the spring, you can draw it. So, spring is stretched and this is the spring. So, if I will take this undeformed position as r0 and I can take this displacement as x. So, I can take a coordinate system, this direction this is x, and position this unit vector is I, and this is y direction, and unit vector I can take j. So, position vector of this mass m, position vector of this mass m can be written as r0 plus, so position vector, so r1 I can write equal to r0 plus xi, and the position vector of point C, already I told you the position vector of, so point C you can write. So, position vector of point C equal to, so position vector of point C is given by r0 plus x plus L by 2 sin theta I minus L by 2 cos theta j. So, from this, by differentiating this position vector you can find the velocity of that mass center. So, V c will be equal to, so if you differentiate this thing, this part is constant. So, it is become x dot plus L by 2 cos theta theta dot I plus L by 2 theta dot sin theta j, and kinetic energy already I told you this is equal to half m x dot square plus half m V c dot V c plus I c theta dot square. So, if you are taking, so in this, so this mass center, either you can take the body or the kinetic energy of this body by taking the purely rotation about this point, or you can take the translation and rotation about the mass center. So, both will yield the same thing. So, if you are taking the mass center, so it will have a translational kinetic energy, that is half m V c dot this, Vc and plus rotational kinetic energy, or if you are taking the rotation about this, then it will be, if I will take this point I, so it will be half I 0 theta dot square. So this I 0 is nothing but it will be equal to m L square by 3. So if you add these two terms, it will give the same expression. So in this case you already know that this kinetic energy is given by this. So this is the expression. So 1/3 m L square theta dot square already you are getting, and this is due to the translation of this, and this is the coupled term. And so the potential energy, now you can find the potential energy of the system. So potential energy due to the spring, so that is equal to k x square, and due to change in position of the rod. So initially the rod was straight, now it has come to this position. So this change in position, so this is the mass center at a distance L by 2. So this angle you have taken theta. So change in position will be this to this. So this length initially it is L by 2 at a distance L by 2. Initially the mass center is here, now it has come to this position. So this is the change in the position of the mass. So potential energy equal to mg into change in position of the mass. So this is equal to mg into L by 2 1 minus cos theta. So this is the potential energy V, and already you know the kinetic energy. So the Lagrangian of the system equal to T minus V equal to this. So the del, now you just take this del L operator. So this del L operator will give you, so x dot square, if you take the del of this, so it becomes 2 x dot into delta x dot. Similarly for this, so you have product of three terms here. So you can write this as m L delta x dot into theta dot cos theta, plus now you just take m L x dot into delta theta dot into cos theta, and the third term will be differentiation of cos. So it becomes minus, so minus m L x dot theta dot m L x dot theta dot sin theta delta theta, and for this it is becomes 1/3 m L square. So this become 2 theta dot delta theta dot, and for these terms, so for these terms this becomes half k into 2 into x into delta x plus mg into half. So mg into, so this term you can write, so this is equal to L by 2. So this is L by 2, and this 1 differentiation 1 is 0, and minus cos theta equal to plus sin theta, and theta differentiation with del. So this becomes del theta. So this term becomes del theta. So now you can take these terms. So this delta L you now know. So you can write this del L equal to m plus m to x dot plus m L theta dot cos theta into delta x dot. Now you have to integrate this whole thing from T1 to T2. So while integrating this thing from T1 to T2, so you have to take this following, or you have to do in the following way. And before that you should find the work done by this non-conservative force, and already you know the position vector of the mass. So this is the rod where the force is a horizontal force F is acting. So this horizontal force, in as it is acting in I direction, so it is written Fi. So work done will be Fi dot this virtual displacement. So this is the position vector, you just find the position vector of this point. So this point position vector will be equal to, so this is equal to position vector of this point equal to r0 plus x plus L sin theta I minus L cos theta j. So this is the position vector of this point. So you have to find delta, so r, so you have to find delta r. So Fi dot delta r, so this is delta r, and you can find this is equal to F into delta x plus Fl cos theta delta theta. So using this extended Hamilton principle, delta L plus delta WNC dt equal to 0. So here delta x would be equal to 0 and delta theta will be equal to 0 at t equal to T1 and T2. So using this expression, so now you have to expand these terms. So while expanding this term, you just note that this delta x dot and this is dt. So while integrating this delta x dot, you can change the, so operator, see this x dot equal to, so delta x dot you can write it equal to delta dx by or del x by del t. So, you can exchange this and you can write it is equal to del by del t of del x. So, this way you can write this delta x term and delta theta term. So, delta theta also you can write del by del t of del theta and you are integrating it with respect to dt. So, it will be the integration. So, the integration will be like this. So, this term I have expressed in this form. So, the first term I have exchanged it d by dt of del x dt, and in the second terms also I have written in the same way. So, if I integrate this first term, so this is the first term I have taken. So, this first term if you integrate it, so that you can take the first. So, m plus m x dot plus half m l theta dot cos theta into d by dt of del x dt. So, this will be equal to, so you just take these are the first function, one as the first function and other as the second function. So, this is the first function you take and this is the second function you take. So, you just integrate it by parts. So, integrating it by parts, so first function remain as it is and integration of the second function. So, d by dt of del x. So, when you are integrating this thing, so it becomes del x only at from t1 to t2. Already you know that this del x at t1 and t2 are 0. So, these terms will, so this term will tend to 0 and the remaining term will minus integration t1 to t2. So, this is the first function remain as it is, integration of the second. So, now minus integration of the second. So, this del x and differentiation of the first. So, differentiation of first will give you, so x dot differentiation is giving x double dot and this differentiation is giving half m l theta dot differentiation theta double dot cos theta minus. So, this contain two terms. So, you will have two terms here. So, minus m l theta dot into cos theta integration, cos theta differentiation is sin theta. So, this becomes sin theta minus sin theta into theta dot. So, theta dot into theta dot giving rise to theta dot square. So, this is equal to half m l theta dot square sin theta dx dt. So, in this way you should integrate it by parts. So, using integration by parts. So, this term you have seen that it is equal to 0 and the remaining term is this. Similarly, you can carry out the second terms. So, it is equal to 1 by 6 m l 3 x dot cos theta plus 2 l theta dot d by dt delta theta dt. So, this is the first function you can take. So, up to this you can take the first function. So, this is the first function and this is the second function. So, integration of the second function d by dt del theta dt. So, this is equal to integration d of del theta. So, this becomes del theta. So, integration of this equal to del theta and so first function into del theta t1 t2 and then del theta into differentiation of this. So, differentiation of this is this. So, this becomes this. So, this is t1 to t2. So, this is the thing. So, this part already you know that this virtual displacement delta theta at t1 equal to t2 equal to 0. So, this part becomes 0 and so similarly you can go for the third term is f minus kx delta x dx. So, you just note that you need not have to go further or integrate it further, you just keep the term in this form. So, something into del x to dt. Similarly, the fourth term becomes this. So, now you combine the terms with del x dt or del theta dt and you just combining that thing, you just write this. So, this becomes this into del x dt plus integration this into del theta dt. Already you know that this del x and del theta are arbitrary as these are the virtual displacement. So, it can take any value. So, this integration to be equal to 0, in that case the coefficients of this del x dt or del theta dt should be equal to 0. So, as the coefficients of these two are 0, you can find the equation motion from this. So, this part will be equal to 0 and this part will be equal to 0. So, these are the equation motion of this system. So, in case of this Hamilton using extended Hamilton principle, so you got the equation motion. So, this is the first equation motion, this equal to 0 and this is the second equation motion, that is equal to 0. So, you are equating the coefficients of del x dt equal to 0 to get the first equation and equating del theta dt equal to 0 to get the second equation. So, in this way you can get the two equations. So, in this case you just see that for this, in this case you are getting the equation motion to be in this form. So, this is m plus m x double dot plus half m l theta double dot cos theta minus half m l theta dot square sin theta minus k x equal to f, and 1 by 6 m l. So, this m l 3 x double dot cos theta minus 3 x dot theta dot sin theta plus 2 l theta double dot plus half m l x dot theta dot plus g sin theta equal to f l cos theta. So, in this way you can find these two equations. So, these equations you just observe that these are nonlinear equations as it contain the product of different terms. So, this nonlinear equation you may make linearization to find the linearized equation. So, you can substitute this for theta to be small. So, you can substitute cos theta equal to 1, sin theta equal to theta, and you may neglect the product of the higher order terms and you can write the linearized equation motion. So, similarly you can find the equation motion, the same equation motion by using the Lagrange principle also. So, by using Lagrange principle already you have found the kinetic energy of the system, already you have found the potential energy of the system. So, you know the Lagrangian of the system. So, after knowing the Lagrangian of the system, then you just use this equation. So, d by dt of del L by del qk dot minus del L by del qk equal to qk nc. So, by using this equation you can find the equation in this case. So, you will get the same equation whatever you have got here by using the extended Hamilton principle. Now, so till now you know the four different methods to find the equation motion of the system. First you know the Newton's second law, second by using this D'Alembert principle, third the Lagrange principle, and fourth the extended Hamilton principle. Generally this Lagrange principle is used for multi-degree of freedom systems and Hamilton principle is used for continuous or distributed mass systems. So, most of the cases for this multi-degree of freedom system or 2 degree of freedom system you should use the Lagrange principle or the Newton's or D'Alembert principle instead of going for this Hamilton principle, extended Hamilton principle. So, now we will see the free vibration of a 2 degree of freedom system. So, free vibration of a 2 degree of freedom system. So, already you have derived the equation motion and you have written the equation motion in this form. So, mass matrix plus, so mass matrix or in matrix form you have written the equation motion in this form, that is mx double dot plus kx mx double dot plus kx equal to 0. So, let me take this simple system, and so this is the spring mass damper system. So, with mass m1 and already I have derived the equation motion for the system, and so this is the system I have taken, this is k, I have taken this is k1, this is k2, this is k3, and I have derived the equation motion for the system, and already you know the equation motion for the system equal to m1 0 0 m2 x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2, this is k2 plus k3 x1 x2 equal to 0 0. Now, I want to study the free vibration response of the system. So, in case of a single degree of freedom systems, you have seen the free vibration response can be written in this form. So, in case of a single degree of free spring mass damper system or spring mass damper system, you have seen. So, this is the mass. So, you have seen the solution to be written in this form. So, your x you have written in this form a sin omega t. So, a sin omega n t. So, you have written. So, where omega n is the natural frequency of the system and A is the amplitude of the response. So, you have written the free vibration response of the system in this way. Similarly, in this case also I can assume the solution to be in this form, x1 equal to a1 e to the power I omega 1 t, and or I can assume it e to the power I omega t, and similarly x2 I can assume it equal to a2 e to the power I omega t. So, I can assume this type of solution. So, in which both the frequency I am assumed to be same. So, in this case you can find this response amplitude a1 and a2. So, now substituting this expression in the previous equation. So, you can write the equation motion in this form. So, you can write, so instead of assuming e to the power I omega t, also you can take this equal to a sin omega t and a2 sin omega t also. So, either you take a1 sin omega t, a2 sin omega t equal to x1 and x2, or you just take x1 equal to a1 e to the power I omega t, x2 equal to a2 e to the power I omega t. Then you substitute this expression in this equation motion. So, if you substitute in equation motion, then you can obtain the equation in this form. So, you can write it in this form. So, it will becomes k1 plus k2 minus m 1 omega square, and so this m1 x1 double dot will becomes a1 omega square e to the power I omega. So, I can write, and this is minus k2. So, minus k2, and then this is minus k2, and this becomes k2 plus k3 minus m2 omega square, and x1 or a1 a2 I have written it a1 a2. So, you can put it a1 a2 e to the power I omega t e to the power I omega t will be equal to 0 0. So, from this equation you can observe that as e to the power I omega t is not equal to 0, and you are interested for a non-trivial solution where a1 and a2 are not 0. So, the determinant of this matrix should be equal to 0. So, you have to find the determinant of this matrix and equate to 0. So, let us take a simple case in which this k1 equal to k2 equal to k3 equal to k, and this m1 equal to m and m2 equal to 2m. So, in this case, so let us assume that this is the case we are considering. So, in that case this equation will reduce to, so this becomes 2k minus m omega square. So, this becomes 2k minus m omega square, and this becomes minus k2, this becomes minus k2, and this is equal to, so this is also 2k minus 2m. So, this becomes 2k minus 2m omega square into a1 a2. So, a1 a2 will be equal to 0 0. So, in this case I have to find the determinant of this to find the non-trivial solution. So, that is where a1 and a2, either a1 or a2 not equal to 0. So, in case of trivial solution a1 and a2 are 0, but as we are interested to find the non-trivial solution, so this determinant part will be equal to 0. So, the determinant of this equation will become, so this is equal to 2k minus m omega square into 2k minus 2m square. So, minus k2 square. So, this becomes minus k2. So, this k2 equal to, already I have taken k2 equal to k. So, this becomes k square. So, this becomes k square will be equal to 0. So, this is the determinant. So, let me substitute this omega square equal to lambda. So, this equation will become, so this is 2k minus m lambda into 2k minus 2m lambda minus k square equal to 0, or I can write this equation. So, this equation I can write equal to 4k square. So, this is 4k square minus 6 m k lambda. So, this becomes minus 2 k m k lambda, then minus minus plus. So, this becomes 2 m square lambda square minus k square equal to 0. So, from this I can write the equation becomes, so from this I can write lambda square, the equation reduces to lambda square minus 3 k by m lambda, 3 k by m lambda plus 3 by 2 k by m equal to 0. So, from this I can find this is a quadratic equation, and solution of this quadratic equation will give me the frequency equation. So, I can have two value of lambda. So, the lambda 1, so I will have this lambda 1 equal to lambda 1 equal to, so this becomes, so this is lambda 1 2 you can find minus b. So, minus minus plus, so 3 k by m minus b plus minus root over b square minus 4 ac by 2a b square, this becomes 9 k square by m square and minus 4 b square minus 4 ac. So, this is equal to 3 by 2 k by m into 1 by 2. So, this becomes, so this is 3 k by m. So, this is 2. So, this becomes okay. So, this is 2. So, 2 into 3 6. So, 9 k square by m square, and this becomes, so from this expression you can see that this is equal to this is equal, this there is a square term here 3 by 2 k by m square. So, this is k by m whole square into 1. So, this becomes 0.634 k by m, and this is lambda 1 and lambda 2 equal to 2.366 k by m. So, I got two value of the natural frequency, one is lambda 1 that is 0.634 k by m and lambda 2 equal to 2.366 k by m. So, from this I can find omega 1, that is the first natural frequency, or omega 1 will be root over, so root over 0.634 k by m, and omega 2 will becomes root over 2.366 k by m. So, in this case I am getting two natural frequencies, that is omega 1 and omega 2. In case of single degree of freedom system, you can recall that you got only a single natural frequency, that is equal to root over k by m. So, in this case you are getting two natural frequency, and substituting these two natural frequency in this equation, 2k minus m omega square minus k 2k minus 2 m square a1 a2 equal to 0 0. So, you can find the expression for a1 and a2. As you can see, this right hand side equal to 0. So, you cannot get a unique solution for a1 and a2. So, taking any of this equation, you can find the relation between a and a1 and a2. So, taking this first expression, you can write this 2k minus m omega square a1 minus k a2 equal to 0, or you can write this 2k minus m omega square a1 minus k2 a2 equal to 0, or a1 by a2 you can write in this form. So, a1 by a2 equal to, so this k2 already I have taken it equal to k. So, this becomes k by 2k minus m omega square, and already I found the two values of omega, or two values of omega square, or two values of lambda. So, by substituting those two values, so you can get, so by substituting the first value, so a1 by a2 you can get, so when lambda equal to lambda 1, so you are getting this is equal to 0.731 is to 1. Similarly, when you are substituting lambda equal to lambda 2, so you are getting two value of lambda, so lambda 2, so this becomes minus 2.731. So, in this case you can observe that in the first case, when the natural frequency or lambda 1 equal to 0.634 root over 0.634 K by M. So, in that case you can observe, or your system will be like this. So, this is the system. So, with this is the original system. Now, when it will have a frequency lambda equal to lambda 1. So, you have observed that when this is moving, so this A 1 by A 2 you have seen it equal to 0.731 by 1. That means, when this x 2 moves a distance 1 unit in distance, so this will move a distance of 0.731. So, when x 2 is moving a distance, or the second mass is moving a distance of 1, the first mass is moving a distance of 0.731. Similarly, in the second case, you can show that, or you can draw it like this. So, when the first mass is moving, so you have these are the masses, two masses. So, in the second case you have seen that this is x 1, this is x 2. So, you have seen A 1 by A 2, A 1 by A 2 equal to minus 2.73 by 1. So, in this case, so when this is moving a distance, so this negative sign indicates that it is moving towards left. So, this is 2.73. That means, when it is moving a distance of 1 in this direction. So, when A 1 or second mass is moving a distance, so this is the second mass, this is the first mass. So, when the second mass is moving a distance of 1 towards right, the first mass is moving a distance of 2.73 towards left. So, in this case, this spring, the second spring will be under tension. So, this spring, so in this way it is moving a distance 1, and in this way it is moving a distance 2.73. But in the previous case you can observe that this spring, both of them are moving in the same direction. It is when it is moving 1. So, this is moving 0.73. So, the spring is compressed. So, in this case the spring is compressed, and in this case the spring is in tension. So, in the first case you can tell that both the masses are in phase, or they are moving in the same direction. But in the second case you can tell that both the masses are out of phase, that is, when one is moving towards right, the other one is moving towards left. So, this is the normal mode. So, when you are normalizing this thing, so in this case, in both the cases we have made this A 2 equal to 1, and we have found the value of A 1. So, in both the cases we are normalizing the second mass, the displacement of the second mass, and in both the cases we are assumed that both the masses are moving with the same frequency and crossing the equilibrium position at the same time. That means, we are taking that they are moving with a particular frequency. So, this type of motion in which we are considering the motion is taking place at the same frequency are known as normal modes. So, we have two normal modes in this case. So, the first normal mode equal to, so this is the first normal mode, I can write phi n. So, this phi 1, or I can write this first normal mode phi 1 equal to, so this indicate the motion of these masses when it is moving with the first frequency lambda equal to lambda 1. So, when it is moving with lambda equal to lambda 1, so these two masses will have displacement 731 and 1. So, this phi 1, this is the normal mode. So, the normal mode I can write for the first mass, the first normal mode equal to 0.7311, and similarly the second normal mode phi 2 equal to minus 2.731. So, I can write the modal matrix P, I can write modal matrix P equal to phi 1 phi 2, and this thing can be written in this form. So, it will be equal to 0.7321 and minus 2.731. So, in this way you can determine the normal mode of a system. So, to determine the free vibration response of the system, so you can use these normal modes to find the free vibration, and you can at a particular time the free vibration can be considered to be the summation of the normal modes. So, the free vibration you can assume to the summation of the normal modes. So, at a particular time the free vibration x you can write will be equal to, so x will be equal to phi 1 a sin omega 1 t plus psi 1 plus phi 2 b sin omega 2 t plus psi 2. So, in this case already you know this phi 1 and phi 2. So, these are the normal modes, and a, b and the psi 1 psi 2 can be determined from the initial conditions. So, given the initial conditions of this mass 1 and 2, so initial conditions represent the displacement and velocities for, so for each mass you have the displacement and velocity. So, you have 4 known quantities, so 2 displacement quantities and 2 velocity quantities. So, 4 known quantities. So, you have here 4 unknowns, that is a, b and psi 1 psi 2. So, you have 4 unknowns and 4 equations for displacement and velocity. So, by solving those equations you can find this a psi 1 and b psi 2, and you can find the response of the system. So, the free vibration response of the system you can find by using these normal modes. So, let us take the same problem, and so in this problem let me assume that this x1, so this x1 equal to, so x1 0 at x1 0 equal to, let x1 0 equal to 5 and x2 0 equal to 1, and these velocity terms are, so x1 dot 0 equal to 0 and x2 dot 0 equal to 0. So, let me, these are the initial conditions for the system. So, taking these initial conditions, I have to determine the response of the system. So, already I know the response of the system, x1 and x2 can be written in this form. So, x1 x2 you can write. So, already I know that x1 x2. So, for the first mode I can write. So, the first mode, this is equal to x1 x2 equal to 0.7311 sin omega 1 t, and for the second mode x1 and x2 already you know this is equal to minus 2.731 sin omega 2 t. So, the general solution x1 x2, so the general solution x1 x2 at any particular time t can be written as a phi 1. So, a phi 1 equal to 0.7311 sin omega 1 t plus psi 1 plus b into minus 2.731 sin omega 2 t plus psi 2. So, here we have to find this a, b and psi 1 psi 2. So, from these initial conditions, so this x1 0, so when t equal to 0 I can substitute this in that expression. So, I can find x1 0 and x2 0. So, this phi 1 I can write. So, taking t equal to 0 I can write this equal to, so phi 1 will be equal to a into 0.7311 sin, so t equal to 0, so sin 0 plus psi 1. So, this is equal to sin psi 1 plus b into minus 2.731 sin psi 2. Now, I can differentiate this equation to get, the velocity terms, and from this I can substitute this velocity at initial velocity 0 0. So, I will get this expression. So, x1 dot 0, x2 dot 0. So, these are already known to be 0 0. So, this becomes, this will be equal to omega 1 a into 0.7311, differentiation sign is cos. So, this becomes cos psi 1 plus omega 2 b into 2.7311 cos psi 2. So from this expression you can see that omega 1 a into this into cos psi 1 equal to 0. So omega 1 a into 0.7311 cos psi 1 plus omega 2 b into minus 2.7311 cos psi 2 equal to 0. So from this expression you can tell or you can find that this cos psi 1 equal to cos psi 2 equal to 0. So this expression is valid. So when cos psi 1 equal to cos psi 2 equal to 0 or psi 1 equal to psi 2 equal to 90 degree. So you can substitute this expression for psi 1 psi 2 in the previous equations and you can get this a1. So this equation you will get, so this is equal to 5 1 will be equal to a into 0.7311 plus b into minus 2.731. So now you have two expressions, so 0.731 a plus minus 2.73 b equal to 5 and a plus b equal to 1. So you have two equations. So by solving these two equations you can find a equal to 2.233 and b equal to minus 1.233. So your equation is reduced to this form. So the resulting free vibration response of the system can be written as x1 x2 equal to 2.233.7311 cos. So sin omega t plus 90 degree is cos omega 1 t. So this becomes cos omega 1 t minus 1.233 into 2.731 cos omega 2 t. So this is the required expression for this free vibration of the system. So you know how to determine the normal mode of a system, and using that normal mode you can find the free vibration response of the system. So let us take some other systems to find the normal mode of that system. Let us take a double pendulum, and for that double pendulum let us determine the normal mode of that system. So for a double pendulum, so this is the initial position of a double pendulum. Now due to vibration, so let it has come to this position, this mass has come to this position, and this mass, the second mass has come to this position. So you can express the motion of these two masses with this theta 1 and theta 2. So this is theta 1 and theta 2. So this is mass m2 and this is mass m1. So let us first determine the equation motion using Lagrange principle, and later we will find the normal mode of the system. So in this case the kinetic energy of the system, to find the kinetic energy of the system we should find the velocity of this mass m1 and velocity of this mass m2. So let this length is L1, this length is L2. So I can draw the force, I can draw the velocity. So for this case the velocity becomes, the velocity is perpendicular to this line. So it will be perpendicular to this line, and this length is L1 and this is theta 1. So this is equal to L1 theta 1 dot. And for the second mass, so this is for the second mass. So the second mass makes an angle theta 2 with the vertical. So it will have a velocity relative to this position which is perpendicular to this line. So it will be perpendicular to this line and will have a magnitude L2 theta 2 dot. So the velocity of this position or velocity of mass m2 will be the velocity of mass m1 plus the relative velocity of mass m2 with respect to mass m1. So it will be the summation of, so this is L1 theta 1 dot and this is L2 theta 2 dot. So the V2 or the velocity of this mass m2 will be equal to the vector sum of this L1 theta 1 dot and L2 theta 2 dot. So, you may use this parallelogram laws to find the velocity, and already you know this velocity V2 can be written as L1 theta 1 dot square, L1 theta 1 dot square plus L2 theta 2 dot square plus 2 L1 theta 1 dot L2 theta 2 dot into cos. So, this angle between these two becomes theta 2 minus theta 1. So, this becomes theta 2 minus theta 1. So, this is the expression for velocity of this mass 2. So, the kinetic energy of the system will be equal to half m1 into v1 square, that is equal to L1 theta dot square, and plus half m2 v2 square. So, the total kinetic energy system I can write. So, T will be equal to half m1 L1 square theta 1 dot square plus half m2, already I have written the expression for v2. So, v2 dot v2, that will be the velocity square of this mass m2, and this will be written as L1 theta 1 L1 square theta 1 dot square plus L2 square theta 2 dot square plus 2 L1 L2 theta 1 theta 2 cos theta 2 minus theta 1. So, this is theta 1 dot, this is theta 2 dot. So, this is the expression 2 L1 theta 1 dot L2 theta 2 dot cos theta 2 minus theta 1. So, this is the expression for the kinetic energy of the system. Similarly, you can have the expression for the potential energy of the term. So, the potential energy of the system can be written as, so potential energy due to change in position of this fast mass. So, the change in position of this fast mass, the fast mass initially has a length of L. So, now it has come to this position. So, change in height. So, this is the change in height of this fast mass. So, this becomes L1 into 1 minus L1 into, so this length equal to L1 cos L1 into cos theta 1. So, this becomes L1 minus L1 cos theta 1. So, change in height. So, this is m1 into g into L1 into 1 minus cos theta 1. Similarly, the potential energy for mass 2 you can find. So, the change in height will be equal to L1 plus L2 minus L1 cos theta 1 minus L2 cos theta 2. So, this will be equal to m2 g into change in height of that. So, this becomes L1 plus L2 minus L1 cos theta 1 minus L2 cos theta 2. So, in this way you can find this T and U. So, using this T and U, now you can write this L equal to T minus U. So, L equal to T minus U you can write, and now applying the Lagrange principle you can write the equation motion, which can be given by this expression. So, you can write, you can find that equation motion. So, this becomes m1 plus m2 L1 square m2 L1 L2. So, this is m2 L1 L2 m2 L2 square into theta 1 double dot theta 2 double dot plus m1 m2 m1 plus m2 into L1 g. So, this is 0. So, this is 0 and this is m2 L2 g into theta 1 theta 2. So, this becomes 0 0. So, by using the Lagrange principle, that is d by dt of del L by del q k dot, so minus del L by del q k equal to 0. So, you can find the equation. So, here q1 I have taken equal to theta 1 and q2 equal to theta 2. So, by taking this is theta 1, this is theta 2. So, you can write the equation motion this way. So, now let us take a simple case in which this mass m1 equal to m2 equal to m, and this L1 equal to L2 equal to L. So, this equation will reduce to this form. So, this becomes m L square to 1 1 1 theta 1 double dot theta 2 double dot plus m G L 2 0 0 1 theta 1 theta 2 theta 1 theta 2 equal to 0 0. So, proceeding in the previous way, I can assume that this theta 1 theta 2 equal to a 1 a 2 e to the power I omega t. I can substitute it in this equation and I can write the equation in this form. So, I can write this equation, or I can assume this equal to x 1 x 2. I can write, let me write x 1 x 2 instead of a 1 a 2. So, I can write this is equal to x 1 x 2 e to the power I omega t. So, if I will substitute this equation in this form, so I will get a equation a minus lambda into x 1 x 2 will be equal to 0 0. So, now finding the determinant of this a minus lambda I. So, a minus lambda I into x 1 x 2 equal to 0 0. So, by finding this so this reduces to a eigenvalue problem. So, either you just find the eigenvalue of this matrix A, or you just find the determinant of A to find lambda. So, either you can find the eigenvalue or the determinant. So, if you find, so this lambda you will get will be equal to 2 plus minus root 2 g by L. So, your omega 1 will be equal to 0.7653 g by L, and omega 2 you can find equal to 1.8478 root over g by L. So, root over g by L you will get. By substituting the first one, you can find theta 1 theta 2. So, theta 1 theta 2 for the first one you can find will be equal to 1 by root 2, and the second one if you substitute, then this theta 1 theta 2 you will find equal to minus 1 by root 2. So, in this first case both the masses are moving in the same direction. If you plot, so both the masses are moving in the same direction. So, when this theta 1 it is rotating at angle 1, so this will rotate root 2, and in the second case when this will rotate an angle theta 1 this will rotate in opposite direction, that is minus root 2. Next class we will study about the coupling or coordinate coupling of the system. Already I told about the coordinate coupling, where static and dynamic coupling system I told. I will solve some problems on this dynamic and static coupling next class. Also I will tell you about the force vibration of 2 degree of freedom system.